In this video, we'll go over 3 more problems about modeling real-world problems. The first one is the ball that is kicked vertically upward, so this is number 1 on the practice problems. It's kicked upward from a height of 2 feet, so we're going to say that the ball's here at 2 feet above the ground, and it's kicked with an initial vertical velocity upward at 15 feet per second. And we're going to use that information to write the function for the model of the height of the ball as a function of time. What is the height after 1 second? So we're going to have the ball go up, and then it's going to come back down. And we want to know, after we've watched it for 1 second, where is it in that path? And then lastly, the last part of the question says, how long is it in the air? So if it goes up and it comes back down, and when it hits the ground here. So that's part C, is how long was it in the air. So first we'll write the equation. Well, y equals the initial height plus v initial t plus 1/2 times gt squared. And if we put in the initial height, we can say that y is going to equal 2, the initial height, plus 15, that's v initial, times t, plus 1/2 times minus 32, that's g, t squared. And we use that because we're in feet, not in meters, so we use the 32. So that's the function. We can simplify it a little bit and say y equals 2 plus 15t minus 16t squared. So that's the answer to part A. Now part B says, when t is 1 second, what's y? Okay, so we changed that question. Instead of 2 seconds, it's 1 second. And so the question is, well, we're going to just plug in. Y equals 2 plus 15 times 1 second minus 16 times 1 second squared, and we find out that y is equal to 1 foot. That means that the ball has gone up and it's come back down, and now it's at 1 foot above the ground. That's what we just answered. Okay, and then the last question says, how long is it in the air? Right, so part C says, when the ball goes up and comes back down, well, y is equal to -2. What is the time when y is equal to -2? Because when the ball hits the ground, it's gone 2 feet below where it started, so y is -2. So we're going to plug into our equation. We're still going to use the equation from part A, but we're going to put in y equals -2. So -2 equals 2 plus 15t minus 16t squared. And that's a quadratic. We're trying to solve for t. So we'll add 2 to both sides so that we get it 0 on one side, equals minus 16t squared plus 15t plus 4. So to solve that quadratic, I graphed it and I calculated the 0, and I found that t is equal to 1.06 seconds. So the ball, after 1 second, had gone up and was here at 1 foot above the ground, and just a little bit longer, 1.06 seconds, is when the ball will hit the ground. Number 2 is about a ski shop. The ski shop sells ski packages. They'll sell 800 packages of these ski packages a season, and each one is $600. Well, if we multiply those, right, we get 600 times 800. This person's making $480,000. And it says that if they discount, if they take $10 off, they will increase the number of sales by 20. That's the information that's given, and we want to maximize the revenue. Okay, well, first of all, we know that the revenue is going to equal the number that we sell times the dollars that we sell them for. So the initial revenue is 800 times 600. Times 600. So initially we have $480,000 in revenue. Now, I've suggested that if you want, make a table to figure out what the equation is going to be. So we start off selling 800 packages at $600, and we find that we multiply those to get our revenue, $480,000. If X is 1, we are going to sell 820, 800 plus 1 times 20, and we're going to sell them for $590, which is 600 minus 10. If X is 2, it's going to be 840, and we're going to sell them for $580. If we say that we have X number of $10 decreases, that's going to be 600 minus 10 times X, and we're going to sell 800 plus 20X. Right, sorry, my stylus, I do not have my stylus tonight here. So 800 plus 20X is how many we'll sell, and we'll sell them for 600 minus 10X dollars. That is what our revenue function is going to be. Okay? And if you graph this, you don't even have to distribute anything out. If you graph this revenue function, what you'll find is that it would start off at an initial value of 480,000 on the axis, and it's going to go up and come down. And the max value on this graph, the max here, is going to be when X is 10, Y is going to be 500,000. So our maximum revenue is going to be 500,000. When X is 10, right, well, think about it. When X is 10, that means that I've taken 10 $10 decreases, so I'm going to sell the packages for $500, and I've made 20 times 10 more sales, so that's going to be 800 plus 200, 1,000 packages get sold that season. Okay? And the last one, number 4, we're skipping number 3 since we did it in class, is that you have a garden, and it has dimensions of 12 by 16, and we want to put a pedestrian walkway around it, and we want to find the width. So I'm going to call the width of this walkway X, and I'm going to draw it like this. What that means is that this outside dimension is 16 plus 2 times X, and this dimension is 12 plus 2 times X. Right? If I walk from here, X, 12, X. That's why it's 12 plus 2X. And the problem says that the total area of this whole thing is 285. Well, the area is going to be length times width. That's going to be 285. But we said that the length is 16 plus 2X, and the width is 12 plus 2X. That's going to equal 285. That's the whole area. So if we simplify this expression, get rid of these parentheses, we have 192 plus, foiling this out, 56x plus 4x squared equals 285. And since it's a quadratic, we have the x squared term, we have to subtract the 285, so we end up with a quadratic that's set equal to 0. That's how we solve our quadratics. And I will rearrange this in descending order, so we have 4x squared plus 56x, and when I do this subtraction here, I get minus 93 equals 0. So you can graph this and find the zeros. You can use a quadratic formula. Factoring is a little rough on this one. I graphed it, and when I graphed it, I found that the only positive 0 was x equals 1.5. So the width of the walkway is 1.5, and the unit was meters in this problem. So the width is 1.5 meters.